What if I told you engineers can predict the future without a crystal ball? How do we know how much electricity we'll need 10 years from now? How can we estimate what happens if every car suddenly becomes electric? How do we even begin to understand the impact of our decisions on a system this complex? The truth is, we don't guess, we model. Engineers use something called system models, tools that help us simulate reality, test ideas, and explore possible futures before they happen. And today, you're going to learn how to think like one of those engineers. Let's start with a simple but powerful idea. We don't actually want energy. We want what energy does for us. Think about it. Nobody wakes up and says, "I want electricity." What they really want is light, comfort, mobility, clean clothes, and freedom to use their time the way they choose. This is where the energy currency model comes in. We start with a resource, something like coal in the ground. Then we use a conversion technology, like a power plant. That gives us a currency, electricity. And finally, that electricity delivers a service, like running your washing machine. So the chain looks like this: resource, conversion, currency, service. Why do we call electricity a currency? Because it's flexible, transferable, and easy to use, just like money. You don't carry gold bars to buy groceries. You use cash or a credit card. In the same way, we don't bring coal into our homes. We use electricity. Let's make it even more concrete. Imagine you want to travel to another city. The resource is crude oil underground. The currency is gasoline in your car. And the service is transportation, getting from point A to point B. At every step in this chain, some energy is lost, but we accept those losses because the convenience and flexibility we gain are far more valuable. That's a key engineering trade-off. Now, let's talk about predicting growth. When a new technology appears, something interesting happens. At first, adoption is slow. Then, suddenly, it explodes. This is called exponential growth. The formula looks like this. In the early stages, this model can be incredibly powerful. But here's the catch. Exponential growth doesn't last forever.
Let me tell you a real story. Back in 1970, if someone used this formula to predict US energy consumption in the year 2000, they would estimate a value of 140. But the real number turned out to be only 99. That's a huge difference. Why? Because nothing grows forever. Not trees, not populations, not technologies. Eventually, every system hits a limit, and that's where the S-curve comes in. At first, growth is slow, then it accelerates rapidly, and finally, it slows down again as it approaches saturation. Think about smartphones. At first, only a few people had them. Then, suddenly, everyone bought one. And now, growth has stabilized because almost everyone who needs one already has it. This is what we model using an S-shaped curve. It's a much more realistic way to think about long-term change. Now, let's go deeper into how systems behave. In energy systems, nothing happens in isolation. Everything is connected. And these connections often form loops. Let's build one together. Step 1, temperature increases. Step 2, people use more air conditioning. Step 3, power plants generate more electricity. Step 4, more CO2 is emitted. Step 5, temperature increases even more. This is called a reinforcing loop.
It's like a snowball rolling downhill, getting bigger and faster over time. Now, imagine trying to fix this. A regulation is introduced to reduce emissions. Sounds good, right? But here's the problem: delay. It takes time to pass laws. It takes time to upgrade infrastructure. It takes time for change to actually happen. And during that delay, the system keeps moving. This can lead to overshooting targets or creating instability. Understanding delays is just as important as understanding the system itself. Now we arrive at one of the most important tools in energy analysis, the Kaya equation. This equation breaks down global CO2 emissions into 4 simple factors. Here's the formula. At first glance, it looks complex, but it's actually very intuitive. Global emissions depend on 4 things. First, population. How many people are there? Second, wealth. How much each person consumes and produces. Third, energy intensity. How much energy we use to create 1 unit of economic value. And fourth, carbon intensity. How clean or dirty that energy is. This equation doesn't blame a single factor. It shows a system. For example, a country with a moderate population but very high wealth can still produce massive emissions. A country with a large population and growing economy can see emissions rise rapidly if efficiency doesn't improve. And a country with low income may have lower emissions today, but that can change quickly as development accelerates. Now here's the key insight.
If we want to reduce emissions, we can't realistically reduce population, and telling people to stay poor is neither ethical nor practical. People naturally want better lives, more comfort, more opportunity, more control over their future. So the real leverage points are the last 2 factors. We improve technology to reduce energy intensity, and we shift energy sources to reduce carbon intensity. In other words, we create more value with less energy, and we make that energy cleaner. That's how real progress happens. So, what did we learn today? We learned that energy is not the goal, services are. We learned that growth is not always exponential, systems have limits. We learned that feedback loops can amplify problems or stabilize systems. And we learned that the Kaya equation gives us a powerful framework to understand global emissions. But more importantly, we learned that the future is not something we wait for. It's something we design. Every improvement in efficiency, every innovation in clean energy, every smarter system we build expands human possibilities while reducing unintended consequences. And that's what great engineering is all about. In the next episode, we're going to explore one of the most powerful tools in modern engineering, life cycle analysis. We'll follow products from raw materials to disposal and answer a big question. Are electric vehicles really as clean as they seem? Make sure you're here for that.